Hello everyone, my name is Anthony Farfan, and the goal of this project is to explore whether physics-informed neural network can more accurately model the nonlinear mechanical behavior of hydrogels compared to a classic constitutive model. Soft biological materials like hydrogels tend to exhibit highly nonlinear mechanical behavior, especially at much larger strains, and traditionally engineers must manually choose a constitutive model to describe that behavior. However, these models often struggle to capture complex behavior like nonlinear strain stiffening. CANS, however, offers an alternative approach. Instead of prescribing a specific functional form, the network learns the strain energy function directly from the experimental data while still respecting the laws of physics. So my research question for this project is, can a physics-informed constitutional neural network better model hydrogel stress stretch behavior than a classic neo-Hookean model? The experimental data used in this project was digitized from a published study by Kilvandi et al., which investigated the mechanical behavior of gelatin-based hydrogels. The experiments included uniaxial tension, compression, and shear tests, but this project focuses specifically on uniaxial tensile data. The original data was reported as engineering strain, which I converted to stretch using the relation lambda equals 1 plus strain. With regards to my assumptions, I am assuming it's isotropic and incompressible and hyper elastic. Now, with regards to model architecture, the neural network learns the strain energy density function, which we denote here as psi. Instead of predicting stress directly, the network predicts the energy, and stress is then computed through a differentiation of the energy with respect to deformation, ensuring thermodynamic consistency. For my project, I chose two different to assess two different CAN architectures. The first being the invariant CAN, where the strain energy function depends on the invariance of the deformation tensor, and the second is a stretch CAN, where the energy is modeled directly as the function of the stretch lambda. Both architectures follow the same physics-informed framework, but they differ in their choice of inputs of the neural network, ultimately affecting how the model learns the material behavior. I chose to evaluate my question across two different experiments, with the first one being data efficiency. Here, I trained each model on different fractions of the dataset and then measured prediction accuracy. The plots showed the experimental data alongside predictions from the neo-Hookean model and the two CAN architectures. Across all training functions, both neural networks models achieve significantly lower and higher R-squared values than classic neo-Hookean model. This indicates that the CAN framework can successfully learn the nonlinear stretch relationship even with limited data. The second experiment evaluates the model's ability to extrapolate. In this case, the models were trained only on a lower portion of the strain range and then tested on higher strains that the model had never seen before. The left plot shows a training region and extrapolation region, while the right plot quantifies prediction error. What we observe is the stretch-based CAN is in green, extrapolates reliably outside the training region, closely matching the experimental stress curve. In contrast, the invariant-based CAN in blue becomes unstable and produces large prediction errors when trained on limited strain data. To summarize, there are three main key findings from the work. First, CAN models capture nonlinear hydrogel mechanics more accurately than classic constitutive models. Second, these models are highly data efficient. Third, the architecture of the neural network significantly affects extrapolation performance. And there are several key directions for future work. One extension would be to incorporate multi-axial loading conditions. Another direction would be to improve network robustness and regularization. Overall, this work shows the potential insights for CANs. Thank you.